recording here. Good morning, good evening. All right, so we're gonna keep going. Oh, thank you. I've been really good about remembering the transcript, but I forgot this morning. We're just gonna keep working through the chapter 2 notes. I suspect it's gonna take us kind of today and the next day, so we'll see how far we get. But that's okay. It's good to have a good foundation for this this stuff. So you've got the chapter 2 notes on here. They're called chapter 1 part 2, but following the new setup of the textbook, this would be chapter 2. So last day on Friday, right, I showed you not necessarily how to enter the GDP data here, right? Although I think maybe we ended up doing that at the end, right? But now that you've kind of worked in R just a smidge, right? You could enter the data just like this. So I would probably copy and paste it because otherwise you might get something weird in there, right? And so copy, paste it in, and then you could work with the GDP data as we work through these concepts. I think I confirmed earlier, but let me just check. Yeah, so where we ended off last day was we ended off talking about the mean, right? So the mean is just the average of a bunch of numbers. In this case, it's the average of these numbers here, which we denote by just GDP, or in general, we denote it by X, right? And so to find the mean, the sample mean, right? Because this is a sample, right? Then we would add up all our X's. So the sum of the X's divided by N, where N is our sample size, right? And so here, just as a little bit of review, right? Not too much, but X bar, which is the sample mean of X, right? Which is just a placeholder for any variable, is the sum of the X's divided by N. And sometimes we'll even put a little subscript I here. I'll do it in orange just to show that it's optional, right? But it's really just saying add up all your X's, right? So the sum of X, right? So all your X's, and then N is, of course, the sample size. I like to start with a formula that you know intuitively, right? So you know how to find the average. You add all the values up and then you divide by the sample size. But now we're introducing all this new notation and potentially terminology, right? Sample size. But it's nice to have that connection. So we're going to keep going and we're going to talk about some other measures of center and then measures of spread. So X bar is the sample mean, so that's a measure of center, right? So I'll call that the end of the review. Not much of a review, right? But it kind of gets us going at least, right? And so let's go back to these notes here. So we found the mean. And we even confirmed it using R, right? And so you've got these little R code chunks and you can just copy and paste the code. If you copy and paste the output, notice that it has the pound sign. And so it would just be a comment. So it wouldn't show up, but just copy the code and then run the code and you'll get the output. Okay, so X bar is the mean, right? Which is a measure of center. Oh, I guess I had a little bit more review, just a tiny bit more review. Sorry. I know someone already wrote that in their notes. Come on. You could start it with recall. That's more review. X bar is the most common measure of center. Okay. If you wanted to emphasize, you could emphasize by saying numerical measure of center, right? Because it's a number value, right? And so we have looked at histograms and we've looked at distributions and we said, okay, we can talk about the shape, the center, the spread, so you can kind of eyeball the center. But in terms of getting an actual value, we calculate the sample mean, right? But notice, keep in mind that the mean is only a useful measure of center. For a normal distribution or for normally distributed data, let's say that. Normally distributed data. Okay. Are there non-numerical measures of center? No. So I guess that's why I didn't say it here initially, but then I threw it in because I want to emphasize that it's a calculated measure of center. So maybe that's what I should say instead. A common calculated, how about that? Measure of center, because we could eyeball it, right? But we're still going to get numbers. So saying numerical, you're right, it didn't really make sense. But calculated, there we go. Now we got it. Good eye. So let's see here. So we have to remember that the mean, although we can calculate the mean, right, for any data, it only really applies as a measure of center for normally distributed data. Okay, and so for the measure of spread that we're going to use for normally distributed data, and here's where we start our fresh page here. So that's the end of the kind of review. For normally distributed data, we use the standard deviation as the most common calculated measure of spread. Okay. So we use the standard deviation as the most common calculated measure of spread. So the standard deviation is going to calculate how far each data point is from the mean, right? So from the sample mean. I'll copy this whole chunk in, copy, paste. Okay. So to denote the sample standard deviation, we use a lowercase s, but typically if we're writing about the standard deviation, then we'll use SD as the abbreviation. So it kind of differs, right? So the standard deviation, I'll abbreviate as SD. Yes, it is. So the standard deviation is essentially how far each point is from the mean, but there's a little bit more, right? And I'll go through the formula here. Okay, so there are kind of multiple formulas that do the same thing, and it depends on, hey, good morning. Bring you up here. Make you feel really awkward. I'm watching you. Yeah. No. Okay, so we've got a couple of different formulas. They're all doing the same thing. So I want to show you both of them just so you can see what's going on. And so what we said, or what I said just now, was that, okay, the standard deviation takes each data point and sees how far it is from the mean, okay? But then if it's below the mean, we get a negative value, right? But we also know that we can't take the square root of a negative number, right? That's illegal math. And so to avoid that, and also to make further adjustments, but we'll leave that alone, we square the values, right? Because what happens when we square a value, it becomes positive, right? It also amplifies larger differences, right? So the further away X is from the mean, by squaring it, right, it becomes even more obvious, right, by squaring it. So then we add up all those differences squared, and then we divide by n minus 1. And it can get confusing because this n minus 1, typically we would just divide by n, right? But and it's a whole proof, but we use n minus 1 for the sample standard deviation, okay? And even more confusing, but I'm going to leave it alone, but I will mention it just for completeness sake. But if you're calculating, if you have the entire population, then you would just use n, but I'm not going to go that far, okay? So for us, we're only calculating sample standard deviations, and so so we use n minus 1, okay? Okay, so, and then we take the square root. What I want to highlight here is that this, everything under the square root, is what we call the variance of x. Okay. N minus 1, in this case, it does have to do with the degrees of freedom, but the reason we use n minus 1 is because we're making an adjustment. So if we only used n, then the sample standard deviation would be more appropriate for the sample mean, because that's where we're going from, but we're trying to find the spread for the population, or trying to estimate it. And so when we do n minus 1, it just becomes a little bit closer to the population mean. And that's a lot, right? So for now, I just want you to remember the formula to use, right? And you're making your own formula sheet, but I'll post a formula sheet for you to work off of, and I have both of these formulas on there. Okay, so just remember to divide by n minus 1. So let's see here. Okay, so I think that answered the question, maybe not really. We'll see. So we leave the variance of x for the next blurb, okay? We like to work with the sample standard deviation instead of the variance, just because the units are back to the units of x, okay? Here, we could also write this as, right, we could rewrite this as s is the square root of the sum of the x's minus x bar squared over n minus 1, right? You could kind of shimmy these, they're multiplying. So if you prefer to look at it this way, that's fine too. In fact, I prefer that. But So how would we do this? If we had to calculate the standard deviation by hand of those data points that we had, right? Then what we would do is, now I don't have it, I'll grab it here. This is just a portion because it got chopped off by the page break. Okay, so it keeps going, okay? But if we were using this first equation, how you would work through it is you would set up, and if you're comfortable working in Excel, then that's an easy way to do it. But if you're in Excel already, then you could just use the standard deviation function, right? It can calculate the standard deviation for you. Just make sure that you choose a sample standard deviation. Or if you're working in R, then it's easy, you'll see. So what you would do here is you would first make a new column where you take each X and subtract X bar, right? They have the same X bar. In fact, we found it earlier. It was 5.1083333333, presumably. So from each value of X, we would subtract that 5.108333. Okay, so I like to make a new column of X minus X bar, right? And so here it would be 5.2 minus 5.108333, 9.4 minus 5.108333, and so on. Okay. And you would find those values. Then what you have to do, right, order of operations here, we have to square each value. Okay. So then I would make a new column, X minus X bar, and square it, right? So I would take the result from the previous column and then I would square it, right? So this becomes 5.2 minus 5.108333 squared. Same thing with the next one, 9.4 minus 5.108333 squared, etc. Then at the end, we want the sum of those values, right? So we're just going to end up with one sum. So here, oops, we could add these up and they would end up being the sum of the x's minus x bar squared. Little tiny there. Hey. Two faces. Fun. Okay. And then you would divide that sum by n minus 1, and then you would square root it to find the standard deviation. Okay. So if you have to do it by hand, it's pretty tedious. And sometimes people prefer this second equation. So let's just talk about the differences between the two, right? And so if we're using the second equation, what you would do is, I'll do kind of a break here. Right, so this is for this calculation here. So many arrows. Yikes. And if I wanted to use this equation, what would I need? It says I need the sum of the x's squared, which means that I need to take each value of x and square it and then add them up. But what's nice is after that, it looks like I have all the information that I need, right? I'm going to have my n, I have my x bar. This is just x bar squared, right? And so I guess I should have little brackets to emphasize, but it's also obvious, right? The only way that it would be n times x bar all squared is if I had brackets. So the lack of brackets tells me that it's only on the x bar. So here, this equation requires a little less handwork, right? And so in the notes, this is how I found it. But I just wanted to show you that you could do it for either equation, right? As long as you know how to read what you need to do. So for this one, confusing. What would we need? We would need a column of the x's squared, right? Which means that we would have 5.2 squared, 9.4 squared, and at the bottom, we would get the sum of the x's squared, right? So in terms of kind of doing these calculations by hand, which typically we don't really need to do anymore, it used to be really important to be able to do it, but now our phones can do it, right? You can just Google standard deviation calculator and there's easy ways to find the standard deviation. So it used to be really important. And I will make you do it. It's more of a mathematical exercise than anything else, right? It's not because it's important for us to know how to calculate stuff, but I'll make you do it just so that we can get comfortable with these formulas and understand what's going on, or maybe not understand. That might be too much. At least see what's happening. Okay? So you have two options, and there are other ways that we could reformulate these formulas, but these are kind of the most common ways that we represent the standard deviation. Okay. And so let's see here. What's next? I think the calculation in R. Oh yeah. So here, right in the notes, and I'm not going to copy it in because we kind of showed it. But in the notes, what I've done is I've just shown all the x's squared, right? So 5.2 squared is 27.04, 9.4 squared is 88.36, blah, 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 blah. And then unfortunately, it crossed the page, right? And so the sum, right? The sum of all these is going to be 349.67. Okay, so maybe I'll copy this in here. Let's do, how can I do this like that? Copy. It's so slow, my iPad, but I restarted it and everything. I don't know. So here, this kept going and going. This is the end of it. Okay, and then so at the bottom we have the sum. The sums, okay, which means that this is the sum of the x's squared. Okay. We also know from before, right? So we know the sum of the x's squared now. We already know that we have a sample size of 12 and we have a sample mean of 5.11. Now I've rounded to 2 decimal places, right? And so here, rounded to 2 decimal places. I use DP for decimal places. Hopefully you guys are okay with that. So if we bring in the formula, right, now we can start plugging in these values, right? Keeping in mind that we are using a rounded value for the X bar, right? And so our value is going to be slightly off of what it would be if we did the calculation using software, right? And then we end up rounding in the end more, right? So it's going to be slightly off. So we need to be a little bit okay with kind of numbers being a little bit off if you're using rounded values, right? Especially because sometimes people will do the calculation by hand and then they confirm it using software. And then they get really upset when it's not the exact same value, but unless you're keeping all your decimal places, they won't be exactly the same. And that's okay, right? But you need to develop that sense of how much off is appropriate, right? If they're roughly the same, then you're good. Okay? So we plug in the values, right? Make sure you're following order of operations. So you would start by squaring 5.11, then multiply it by 12, and then subtract it from the sum, and then divide by 11, and then square root. Don't forget to take the square root, right? So here, what we see is that later, everything under the square root is going to be the variance, right? And so here, the variance of x should be about 3.302254545, etc. probably. All right, but it's only showing so many decimal places. So we'll see the variance and we'll confirm it later, but that's what it should be. Okay, so the sample standard deviation that we've calculated by hand is 1.82 once we round to 2 decimal places. Now, okay. So we can confirm it using R, right? And so here we can use this SD function, the standard deviation of GDP, right? So just as a refresher, you're going to read this as the standard deviation of GDP, right? That GDP data set that we entered. I just want to emphasize the of because I find it's going to be really useful later on, right? When we start to read these functions as if they're function notation, then it makes more sense, right? The standard deviation of GDP is 1.8198. Notice that they're just slightly off, right? But once we round to 2 decimal places, then they're the same. And so they're close enough, right? So this is slightly different than our result, but remember our result uses a rounded value of x bar, whereas R is going to keep all the decimal places for everything, right? Okay. So if we have to find the variance, let me grab this here. The key thing about the variance is that it is just the standard deviation squared. So the sample variance is the sample deviation squared, okay? So usually we just denote it by S squared is the sample variance. And it is just S squared, okay? Which means that S is the square root of S squared. So S is the square root of the sample variance, which we saw, right? I kind of highlighted that earlier. Okay. But working the other way, then the sample variance, I guess I have it here, can only say the same thing so many times. So I'll hold off there. Okay. But the sample variance is just S squared. So you could go back and you could square it. Notice that so we're using a rounded value here, and then when we square it, it's a little bit off from what I highlighted up here, right? 3.31022. So if you wanted to, you could just save that as the variance, right? But here, if we use a rounded value of S, That's okay, right? Especially if we're doing hand calculations. If you have a value of S, you can use the rounded value. Usually we round to at least 2 decimal places. And so let's see here. So in R, there's a variance command. Let me bring it in. So we find that the variance, and this is using just all the decimal places, using all the proper values, we find a variance of 3.311742, right? Remember, that's slightly off of what I highlighted earlier, but that was using a rounded value of X bar, right? So we've got these, all these different values, but they're all different because of rounding, right? And so that's important to keep in mind. So try to use as many decimal places as you want, but if you're doing calculations by hand and you've already found a value, you're allowed to use that rounded value. Okay, so let's see here. A little note about the variance. Is that depending on which field you're in, some disciplines prefer to use the variance in their calculations, right? So some disciplines will only talk about the variance versus the standard deviation. We're going to use the standard deviation in our calculations. It simplifies things specifically. So just as a side note, we prefer to use the standard deviation because the units are more obvious. So the units for the standard deviation are the same as the units of X, okay? Because the units are easier to interpret, is what I'll say, easier to interpret. Okay? So the units for S are the same as for X. Okay? So in terms of the standard deviation of the GDP, now I have to refresh my memory what the, I think it's the percentage, the annual percentage. Oops, wrong one. Where do we introduce it? Here. So the GDP units is percent per year, right? So the units for X is percent per year, which means that the standard deviation also has a unit of percent per year. Okay. What's tricky about the variance is that the X's are squared, right? And so for the variance, the units would be the percent per year squared. And that's hard to think about, right? And so that's why we prefer to just talk about the standard deviation, because it's easier to understand the units. So the GDP, when X is the GDP, the units are percent per year, right? So the units for X, or the units for S, will also be percent per year. Okay. Whereas the units for variance are squared, or are the squared units of X. The units for variance are the squared units of X. right? So it would be percent per year squared. Do square brackets. Did a bracket as a side note and then square brackets to show that it's all squared. But of course, it's kind of implied, but right. And so that's the hard part about the variance, is just interpreting those units. Whereas if we're talking about the standard deviation, then we've taken the square root, and so we can just talk about the units. Okay, good. Scroll back down. Oh yeah. You can ignore the stem and leaf plot. The stem and leaf plot is just a poor man's histogram. So I'll do that. I'll bring it in and just make a note here. But I don't really want to do it. I think it's really silly to do. Not doing, but it's in the notes. So if you wanted to, you can look at it. A stem and leaf plot is a poor man's histogram. Okay, and so is the standard deviation sometimes, how'd you get the omega in there? That's really impressive. We use the standard deviation. So the standard deviation is the population standard deviation is sigma. Option Z. Wow, cool. It's awesome. Everyone's trying it. I'm like tempted to do it. Nice. Yeah, everyone's like, okay. So I haven't seen omega. I'm trying to think back to kind of the hardcore days. Those are long gone. No. Omega. It's not ringing a bell, but we do use sigma for the population standard deviation and sigma squared for the population variance. Cool. And you know what? Instead of deleting it, I'll just put it up. Whee! Put it up here somewhere. There's a good spot. Stuff it in a drawer. But it's good to have, right? Now you've got me kind of, I'll have to look into it, possibly, but it depends on the field usually. Okay, so a stem and leaf plot is a poor man's histogram. So you can imagine no computers. So we need to know, oh yeah, question? Jasper, did you have a question? No? Okay. Just saw it's a high five. Okay, so a stem and leaf plot is a poor man's histogram. So take yourself back, there are no computers. We still need to know what the distribution of the data looks like. Yeah, so it totally looks like an old age tally, and that's exactly what it is, right? Remember how we built the histogram is we say, okay, you belong in this bin, you belong in this bin, you belong in this bin, and then the bins all kind of build up, right? And that's exactly what the stem and leaf plot does. There's a lot of theory on how do you construct a stem and leaf plot. that I don't want to, yeah, done. You did it. Stem and leaf plot. That's exactly what it is. So it's just a way to visualize the distribution, right? But because, again, our phones can make a histogram really, really easily, we don't need to do this anymore. The instructions are there, and I'll show you what it looks like. And hilariously, ours still can produce a stem and leaf plot, but right, so typically if we made one by hand, this is what it would look like. So some important notes are that each value has to take up the same amount of space, right? So imagine you're building up these bars, right? But here, I'll just use the R output. It looks a little bit different because they've kind of streamlined how they build their stem and their leaves. And so here, this is the stem, and these are the leaves, leaf, stem and leaf, right? And so here, how you would read this is there was a value of 29, a value of 22, a value of 29, or maybe it's 2.9, 2.2, 2.9. It would be the context of the data that would tell you how to read these, right? So here in this case, it says the decimal point is at the bar. And so 2.9, 2.2, 2.9. And so all the twos were put into the same stem or onto the same stem. And then you would read them that way. So it's important that you have equal spacing between the stems. But when we look at this, and I wonder if I can do it, paste image, and then I wanna, fun. Usually I just make you turn your head, but now I can just turn it on the screen. So here, when I look at this, right, I can get a pretty good understanding of, and maybe I shouldn't do it so extreme here, of the data, right? So that's the point of the stem and leaf plot, but it looks like a histogram to me, right? So here, I would call this approximately normal. It's a little bit harder to figure out where the center is, but it looks like it's around 4.5-ish, right? So it's a little bit harder. But in terms of the shape, I would say it's approximately normal. So I think one thing I forgot to mention, or just haven't mentioned yet, is the smaller the data set is, the more generous we are with calling it approximately normal. So what I mean by that is this looks really good, right? And it looks approximately normal. But even if it was, if we did have kind of a longer tail here with small data sets, I'm hesitant to say that it's skewed, right? I would want to say with a larger data set, then I can feel more confident in the shape, right? The more data we collect, the more smooth our distribution becomes, right? And the more reliable our distribution becomes. So if you have a small data set, then we're more forgiving about the shape. And we can usually just argue that it's approximately normal. Okay. So for small data sets, just as a side note here, for small data sets, we can be more forgiving about the shape and call most distributions approximately normal. Remember, we're always trying to argue that we have an approximately normal distribution because later on, a lot is going to hinge on that. Okay. And so usually my go-to argument is it looks approximately normal because if I collected more data, I think it would even out, right? I think it would kind of smooth out and approach a normal distribution. So what does this distribution look like if we have the histogram? And I'm just going to scroll down a little bit more here. You can ignore part of it. So notice that there is just a hist option, and it'll just produce a basic histogram of GDP. Okay. There are cooler ways of generating plots, but for a lot of things, if you just need a quick look, then the base package histogram is fine, right? And so depending on what other courses you're taking, right, you might be learning ggplot. ggplot is way more sophisticated for building plots, and it basically takes a layered approach. So first we lay out the axes, and then we lay out the data, and then we kind of tweak it to look beautiful. I'm just gonna scribble that out so it's not confusing. But this is base, I just call it the base function. Base R for generating a quick histogram. So now we can see that we've got this kind of the same sort of shape that we saw. And notice I'm cutting it off here because I suspect that it's going to calm down if I collected more data, right? It would kind of even out. This would get larger and just kind of smooth it out. So I did cut through it on purpose. So if we look at this shape, right? Do I think that it's skewed? I like the word perfectly, but I'm not sure what it means in this case. But so here's my argument. Here, even though it looks like we have a skewed distribution, what I would argue is that because of the small data set, I would say it's approximately normal with the exception of an outlier, okay? Because remember, you're always trying to push for a normal distribution, and then you're trying to explain away reasons why maybe it's not, but you're just acknowledging those. So in terms of the shape here, I would say it's approximately normal. Or maybe I'll do the full blurb that I would do. So imagine I'm writing a report, and so here's what I would write. I would write the small data set where did I want to say the small data set? Let me come up with a better way of saying it, because that way you can have it later too. So the distribution, the distribution would likely approach the normal distribution with a larger data set, right? So if a larger data set were collected, it would likely approach a normal distribution. Remember, we're trying to push for a normal distribution. So whatever you need to do, with a larger data set. Okay. Or we could say the distribution looks approximately normal with the exception of an outlier, of a potential outlier in the upper end. Usually we like to highlight where values are. Now this is pretty typical, right? GDP has to do with money. So as soon as we're talking about money, things tend to be a little bit skewed. But in this case, you're trying to argue that you have a normal distribution, right? And so here I would say that this looks almost perfectly normal with the exception of this outlier, right? And so that we could maybe treat that one on its own or something like that. Okay. And so different options, right? You could argue, well, if I collected more data, it would probably smooth out and look like a normal distribution, or just flat out, it looks like a normal distribution with an outlier. Okay. Good. Oh yeah. So here, right, our descriptions, yeah, so you could use descriptive terms like unimodal, right? Meaning it has one mode. But remember, when we say normal distribution, a normal distribution is unimodal and symmetric. And so by saying that, you don't need to mention the mode. But if you do find that you have clear, distinct bimodal distributions, then you would mention that, right? But we're not going to see bimodal distributions that often in this course, right? And what we said about bimodal distributions is that you probably have two groups that you should split up before you analyze them. Okay? And then you have two normal distributions. So good. I feel like I touched on that. Okay, so then if you have a normal distribution, then you can calculate the mean as your center. Right here, we're just eyeballing the center. It's around kind of 4 or 5-ish, right? It's really just a matter of conveying, is it in the 4 or 5 range, or is it in the 14, 15 range, right? So it's not going to be that precise, right? We just want a rough approximation of where the mode is. So you could mention it in that way, I guess. Okay. So in terms of the shape here, when I look at this shape, whoa, catch up here. When I look at the shape of the histogram, and then I look back at the shape of our stem and leaf plot, they're pretty similar. Our stem and leaf plot is a little bit more condensed, but in general, we get the same shape. And so you could use the stem and leaf plot, but it's easier for us to make histograms now, or at least to read them. So I would just stick with histograms. But now you've seen stem and leaf plots and they're cute, but no. It's like if you're stranded on an island and you have to look at the distribution of something, then you can make a stem and leaf plot. All right, so we've talked about normal distributions. We use the mean and the standard deviation. If we have a clearly non-normal distribution, we said that the better measure of center is going to be the median. Okay, so the median is the central value. Okay, so it's the data that splits, or it's the data point or the data value that splits the data in half. Okay, so let's see here. What would we need to do? We would need to sort our data from smallest to largest. Typically, you could go the other way, but usually we just sort from smallest to largest. And then you have to find the central value, right? It's the value that splits the lowest half from the upper half, okay? So there are technical ways of doing it, but I like to use the patent pending boop, boop, boop method. Kind of did like a wavy thing, but I'm okay with it. So I like to use the boop, boop, boop method if I'm doing these things by hand. Okay, and so to find the median, you're first going to sort your data from smallest to largest. Okay, and then what you're going to do, very technical, is you're going to take two fingers, one on each end, and then you're going to boop, 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 boop into the middle. And then you find the middle value. Okay, so patent pending, boop, boop, boop method. No, it's not pending, but I should. I've taught it enough that people know the boop, boop, boop method. I will say that technically, okay, so here's the little footnote to the finding the median in the notes is I use these simplified steps, of course. Technically, we would say that the position of the median is at n divided by 2 if we have an odd sample size, right? Or at n plus 1 divided by 2 if you have an even sample size. Notice that this only gives you the position of the median. It doesn't actually give you the value. Whereas if you're boop, boop, booping your way in, then it just tells you the value. So I just think it's easier. But I mean, technically we should be using, I should be teaching you this, but I find it's overly complicated for what it is, right? Of course, software is going to be able to find the median. In fact, we're going to use a slightly more simplified method for calculating the median if we land on two values at the same time, right? So in the middle, we boop, 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 and then we might end up on two values. How we're going to calculate the median is just taking the average of those two values and using that as our median. Whereas R and Excel, I think they use a weighted approach. So if they're not equidistant apart, it will kind of move appropriately. So it might come up with a slightly different value, but typically they're the same. So let's see how this goes. So we've got our sorted data. Okay. And you know what? I'm going to move this. Hey, what the? There. So here we've got our sorted data. It's been sorted from smallest to largest, right? And so especially if I'm doing these, I would write out the values, right? And make sure that I have 12 still. I don't want to be missing one. And then I typically write across like this, but here we would start at the bottom and the top, and then now we're going to boop, boop, boop our way in. It's with only one pointer. I'll show you one pointer, but I'm doing the same thing on the top. So try not to go cross-eyed here because it can be tricky, right? Boop, boop. Hey, I have to start over. Anyways, I'll tell you this. We end up at 4.6 and 4.7, right? And so if you boop, boop, boop your way in, just being really careful, and you can confirm it, right? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Okay, good. Because it's kind of tricky, right? You got to keep your wits about you. So here, what we do is we show that this is the median by drawing a circle around both of them. And then the median is going to be 4.6 plus 4.7 divided by 2. Confusingly, right, we use the average as the median. That's confusing, right? Just don't think too much about it. 4.65, because they're kind of evenly spaced. Okay, good. So what if we had, hey, I keep going to the wrong. So we can confirm it using R. Of course, there's a median function and it works out to be the same. Oh yeah, show the boop, boop, boop method once more. You got it. In fact, let's do it together. But what I want to do is I want to remove one of these data points. Okay, so I'm just going to chop off the smallest data point, I think. Let me just make sure, compare it to, oh yeah. So if we remove one data point, right, like the 9.4 value, what we get, right, we're going to find that the median is 4.6, so it's a little bit different. So what I'm going to do is I'm going to write out the sorted data. I'm going to write it here so that I can see the numbers, have the same numbers on the screen, but then I'm going to move it down below. Okay, so I'm going to write these out. 2.9, 3.2, 3.9, 4.1. Notice that they're sorted, right? 4.4, 4.6, 4.7, 5.2, 5.4. I need more room. Okay, 5.4, 6.2, 7.3. Okay. So now I'm omitting the 9.4. So now what you're going to do, so this I find is a little bit easier to look at, right, than moving kind of down and up. But so now take your two fingers and start at 7.3 and 2.9. I've got my finger on 2.9, and then I'm going to boop, 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 boop. And I land on a number, which is 4.6. So what it's going to look like is boop, 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 boop. So here the median is just the 4.6. It is fun, right? Boop, boop, boop. I know, now we have software, so we don't even get to do it that much. Boop, 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 boop. Right? But it's a good exercise, and it highlights that it is the central value. So how would we alter our data set in R? That's the question. How do I lob off a data point in R? So I want to show you how to do that. By bringing in the code here. So if I have my GDP data set, okay, presumably GDP has been sorted, okay? which I don't think I've shown, assuming GDP has been sorted. Okay, how we can call just a portion of GDP is we can say that I want GDP, and notice that these are square brackets. So just 1 to 11. So data points 1 through 11. So here, what this says is produce GDP with observations 1 through 11. Okay, and then what I've done is, instead of always just calling it this, which I could, I've saved it as GDP 11 points. So now I have this new data set, which I can refer to as GDP 11 points versus GDP, which has the full 12 points. Okay, so now I can use the median of GDP 11 points to find 4.6. Yeah. All right, nice. Yeah, so the reason I'm showing you both is because we're likely just going to use software, right? But I want you to know that you could just do it by hand if you wanted to. But often for huge data sets, right, especially if you have like more than 15 points. So let's say you have 20 points, that would be annoying, right? Sorting them by hand and kind of booping our way in. No, thank you, right? And so I just want to show you how to do it by hand, but also how to do it using software. So hopefully that answers that. Okay, nice. Okay, so let's see here. For non-normal distributions, so in our case, they're going to have to look really non-normal. Okay. We use the median and the interquartile range, which I'll introduce next. The interquartile range is the distance between the quartiles, but we'll get there. So we use the median and the interquartile range for non-normal distributions, right? Where the median is the center and the interquartile range is the spread for non-normal distributions, because they're resistant to outliers. Okay. So the mean and the standard deviation are not resistant to outliers, meaning that they're going to be pulled towards those extreme values. Okay. So what we're going to find is that if the mean and the median are roughly the same, right, we can usually assume that we have a normal distribution. Okay, so what happens is that we have in the case, and I'm pretty sure I've drawn this earlier, but now that we've seen them all in action, can draw them out. So here in the center, if we have a normal distribution, we have the mean, which is also the median, which is also the mode. And maybe I'll bump this over so I can do them side by side here. Dink. Okay. Whereas if I have a clearly skewed distribution, like that, okay, what's going to happen is that we have these extreme values. Imagine if you are looking at these numbers here, okay, if you have to find the average, right, we found it was 5.11, let's say, right? Use the rounded values. Now imagine this 9.4 is changed to 94. What would happen to the average? It would blow up, right? Because it's going to get pulled in the direction of the tail. Same thing with the standard deviation, it just gets way too large. Whereas the median, if this is 9.4 or 94, the median doesn't care, right? Because we're just booping our way into the center. And so that's what we mean by being resistant to outliers, is that the median just kind of holds steady and it kind of ignores extreme values in the tails. So what that's going to look like is that now we have kind of the median and the mode tend to hang out around the same place, whereas the mean, the mean is always pulled in the direction of the tail. So note the mean, that doesn't really, the mean is always pulled in the direction of the tail. Yeah. Good. So what could we do then? If we have the mean and the median, then we could compare them, right? So for example, if the median is 4 and the mean is 1.2, describe the distribution or the likely distribution. So I'm getting these direct messages, but I think they're really good questions. So I would prefer it if you put it in the general chat so that everyone can see. So the question was, can you explain why the mean is pulled in the direction of the tail? Because that was unclear. So what happens if you just imagine this data set here, right? And so, nice, back on track. So good. So here, if this value was something like, let's change it to 17, right? So now imagine instead of taking the average with 7.3, then we would have this 17 in there, right? Which would be part of our sum. And then we're still dividing by the same number. And so the mean is going to get pulled in that direction. Whereas for the median, when I'm booping my way in, the median doesn't care that this was 17 or 7.3 or whatever. It only cares about the central value, right? And so that's why we say it's resistant to outliers. Okay, so we got a couple of different options coming in here for this example. So if I have to describe this, the most likely distribution, right? What I like to do is I like to draw something similar to this and just kind of visualize it. So I've got the mean is 1.2, so it's going to be to the left of the median, but the median is always going to hang out at the lump, right? And so what it's going to look like is I would have potentially this type of distribution, right? Where it's the median, median is 4, and maybe here the mean It's 1.2. So it would be skewed. Which way is it? Right skewed, left skewed, right skewed, left, right? Because it's always skewed in the direction of the tail, right? And so I mentioned it before, but it's really important because most of us want to talk about the lump, right? But in statistics, we're going to be more concerned with these tails, right? They're more of a problem for us. And so that's why we say it's skewed to the left. So lock it in. It's skewed to the left or in the negative direction if you wanted to, right? So this would be skewed left, right? Because we've got this kind of tails running to the left. So just knowing the median and the mean, right, we can compare those two values, and if they're roughly the same, they don't have to be exactly the same, but if they're roughly the same, we can typically assume that we have an approximately normal distribution, right? And so if the mean and the median are roughly the same, we can conclude we likely, and there are scenarios where we don't, especially if we have a symmetric bimodal distribution, that would be a curveball, because then if it's symmetric, then the median would be in the middle as well as the mean, but that's very rarely going to happen, right? And so we likely have a normal distribution. So even with just a numerical summary of the data, right, we can draw conclusions like that. We can say, okay, well, I can compare the mean and the median and have some rough idea of the distribution, right? We would confirm it with a histogram, for example, right? But just to get a quick idea of the distribution, we can just look at the mean and the median and how they compare. Okay, I know I'm out of time. 1 minute to go through the quartiles. If we have a range of values on the extreme, so very low values, does it affect the shape of the distribution? It would. So what I'm imagining here is that you would have a distribution maybe like this, where maybe you have kind of a lump of data down here, and then most of your data would be here, right? In terms of kind of a histogram here. Is that kind of what you're describing? Okay, yeah. So then we would probably want to consider these two, consider splitting them up. Maybe there's some categorical variable where we could split them up. But typically what we would generalize this shape is just like this, right? Fat tail distribution, yeah. So that can happen. And they kind of give us a little bit of trouble because now this is definitely skewed. It's skewed to the left. And there's no way that I could argue that this is a normal distribution, right? I could argue that this here is a normal distribution, with the exception of all these outliers making a mess, right? And so it's not something that we're going to deal with in this course, but it is something that can happen. And if you see something like this, my first step would be to try to split these up, right? Try to identify this group from this group and see if you can kind of tease them apart so that you don't have to look at them together, right? Because probably what's going to happen is if you zoom in on this group, you might have kind of a mini normal distribution here. And if you zoom in on this group, right, you might have a mini normal distribution. Yeah, a fat tail distribution does exist. And it just allows for the potential of more things happening in the tails. But it's also a funny name. Oh my gosh, I'm out of time. And no one told me. You guys are all interested in the fat tail distribution. Anyways, if you have any questions, let me know. Otherwise, I'll see you on Thursday. And I'll end this recording here.